Welcome you all to ITE 1222 System Analysis and Design course. I am Ishara Devendra, lecturer at the University of Moratuwa. In today's lesson, you are going to learn about data flow modeling. Before moving forward, let's take a moment to get familiar with the standard color coding scheme we have been using throughout this course. Now we'll first look at the learning outcome of this course. After completing this lesson, you will be able to describe data modeling concepts with data flow diagrams, explain the rules for data modeling, explain the concepts of leveling and balancing in data flow diagrams, and develop data models for a given scenario. Let's see why we need to learn about data flow diagrams. Because a data flow diagram shows the way information flows through a process or a system. So, what is a data flow diagram? A data flow diagram maps out the flow of information for any process or a system. A data flow diagram uses various symbols to show how the system transforms input data into useful information. Simply, we can say data flow diagram shows how data flows within an information system. A set of data flow diagrams represents a logical representation that shows what the system does without discussion how it does it. It is important to note that data flow diagrams do not show program logic or processing steps in the information system. Data flow diagrams help system designers and others during initial analysis stages to visualize a current system. So, data flow diagrams represent the following: external devices sending and receiving data, processes that change the data, data flows themselves, and data storage locations. When communicating how information data flows through systems, data flow diagrams are the method of choice over various other technical descriptions for these reasons. Data flow diagrams are easier to understand by technical and non-technical audience. And also, data flow diagrams can provide a high-level system overview, complete with boundaries and connection to other systems. Data flow diagrams can provide a detailed representation of system components. Let's see why we need these data flow diagrams. The foremost reason is that the data flow diagram is a very simple formalism. As a result, it is simple to understand and use. A data flow diagram hierarchically describes several sub-functions commencing with the collection of high-level functions of a system. A hierarchical model usually starts with the straightforward and abstract model of a system and the different details of the system. To show the data flows within an information system, we can use symbols on data flow diagrams. Data flow diagrams use four basic symbols that represent processes, data flows, data stores, and entities. Several different versions of data flow diagram symbols exist, but they all serve the same purpose. So these are entity, process, data store, data flow, and activity. So we'll go through one by one. The first symbol is the entity. Entities either produce data to the system or the source or accept data from it. Entities produce and consume data that flows between the entity and the system being diagrammed. They can represent another system or indicate a subsystem. Entities are usually represented as rectangles. In this image, you can see how we can represent the entities in a data flow diagram. Next symbol is the process. Process is known as an activity that changes or transforms data flows. It is also known as an activity, work, or action. Since they transform incoming data to outgoing data, all processes must have inputs and outputs on a data flow diagram. Process names normally describe the transformation which can be performed by people or machines. As an example, we can say some processes like submit payment, get invoice, and activate records. In this image, you can see the notation to represent a process. So as the notation, a rectangular box is used and may be labeled with the reference number. Location of where in the system the process occurs and a short title that describes its function. Next symbol is the data store. Data stores could consist of files held long term or a batch of documents stored briefly while they wait to be processed. It does not generate any operations but simply holds data for later access. Input flows to a data store include information or operation that change the stored data. Output flows would be data retrieved from the store. In this image, you can see the notation to represent the data store in a data flow diagram. This is an example of how to represent the data store in a system. There is a process as enter order and two data stores as open order file and PO file to change the stored data. And you can see another data store as customer data to retrieve the customer data from the store. So this is an example for data store element in a data flow diagram. Next symbol is data flow. Movement of data between entities, processes, and data stores is represented with an arrow symbol, which indicates the direction of flow. These data flows are the inputs and outputs of the data flow diagram. A data flow represents the interface between the various components of the data flow diagram. Input and output data flows are labeled based on the type of data or its associated process or data store. In this image, you can see how to represent a data flow. There is a process and a data store, and the movement of the data between process and data store is shown by the arrow. The name is written alongside the arrow as order data. So this is how we can represent the data flow in a data flow diagram. This figure shows the data flow diagram symbol descriptions and notation as a summary. So you can get more understanding on the data flow diagram symbols by referring this table. Now you have a better understanding of the symbols of data flow diagrams and the representation of them. Now we will discuss some rules that we need to follow when designing the data flow diagrams. Here are some rules. Data cannot flow between two entities, and data cannot flow between two data stores. And also, data cannot flow directly from an entity to a data store. A process must have at least one input data flow and one output data flow. A data store must have at least one input data flow and one output data flow. Here we'll discuss some rules with the representations. The first image shows a rule as no process can have only outputs or only inputs. It means the processes must have both inputs and outputs, and the process labels should be verb phrases. Next rule is that all flows to or from a data store must move through a process, and data store labels should be noun phrases. This represents that bidirectional flow between process and data store is represented by two separate arrows. The fork data flow must refer to the exact same data item from a common location to multiple destinations. This represents that joint data flow must refer to exactly the same item from multiple sources to a common location. And data flow cannot go directly from a process to itself, must go through interweaving processes. So these are the rules that we should follow when designing the data flow diagrams. Although all data flow diagrams are composed of the same type of symbols and the validation rules are the same for all data flow diagrams, there are three main types of data flow diagrams. These are known as context diagrams, level 0 data flow diagrams, and level 1 or lower data flow diagrams. Let's discuss them. First diagram type is a context diagram. Context diagram data flow diagrams are diagrams that represent an overview of the system and its interaction with the rest of the world. The context diagram is employed to confirm the context and boundaries of the system to be modeled. It includes identifying things that are inside and outside of the system. And what is the relation of the system with these external entities? The diagrams does not contain any data stores. When constructing context diagrams, you may find the following steps useful. The first one is identify data flows. Then identify external entities by recognizing sources and recipients of the data flows that lie outside of the system. Then draw a process box denoting the entire system. Draw external entities around the process box. And finally, add the data flows between the external entities and the system box. This is how we can create a context diagram. In order to create the context diagram, external entities and data flows must be identified. This figure represents a context diagram for a food ordering system. So you can refer more examples for context diagrams. As described previously, in context diagrams, the entire system is represented as a single process. So level 0 data flow diagrams represent a more detailed view of the system than context diagrams. It shows the main sub-processes and stores of data that make up the system as a whole. We can think of a level 0 data flow diagram as an exploded view of the context diagram. This is an example level 0 data flow diagram for the food ordering system. In this diagram, we can see main processes, data stores, and the data flows in the food ordering system. We have already seen how a context diagram can be decomposed or exploded into a level 0 data flow diagram. This same process can be applied to each process appearing within a level 1 data flow diagram. A level 1 data flow diagram notates each of the main sub-processes that together form the complete system. In data flow diagram modeling terms, we talk of the context diagram as the parent and the level 1 diagram as the child. We can think of level 1 data flow diagram as an exploded view of the level 0 data flow diagram. The following steps are recommended to support the development of level 1 data flow diagrams. First, identify sub-processes. Then, draw the data flows between the external entities and processes. Identify data stores and represent them in the diagram with the proper name. And add data flows that are moving among processes and data stores. Each data store must have at least one input data flow and one output data flow. Finally, check the diagram for correctness with the help of the rules mentioned previously. So this is how we can create a level 1 data flow diagram. Here is an example to understand the relationship among levels of data flow diagrams. First diagram is a context diagram. Then you can see the level 0 data flow diagram. Level 1 data flow diagram is the process 2 is in the next diagram. Accordingly, we can add all the sub-processes into other processes also. Last diagram is the level 2 data flow diagram for process 2.2, and it is an exploded view of the level 1 data flow diagram. From this example, you can see the relationship among levels of data flow diagrams. Here you can see the context diagram, level 0 data flow diagram, level 1 and level 2 data flow diagrams. Let's discuss what is defined by the leveling and balancing. Leveling and balancing techniques are very important for developing lower level diagrams. Leveling is the process of drawing a series of increasingly detailed diagrams until the desired degree of detail is reached. Leveling displays the information system as a single process and then shows more detail until all processes are functional primitives. Balancing maintains consistency among the entire series of diagrams, including inputs and output data flows, and data definitions and the process descriptions. The following diagram is an example of a context diagram with one input and one output. These inputs are input A and output is output B. When this context diagram is decomposed into level 0 data flow diagram, the consistency of inputs and outputs should be properly maintained. This concept is known as balancing of a data flow diagram. It means the inputs and the outputs should be the same after doing the decomposition. How will this data flow diagram be unbalanced? In this figure, you can see the context diagram has one input and one output as input A and output B. The level 0 diagram has two inputs and one output. So we can say this is unbalanced because the process of the context diagram has only one input, but the level 0 diagram has two inputs. So this is why we can say it as the unbalanced data flow diagram. From today's lesson, we have discussed data modeling concepts with data flow diagrams and the rules for data modeling, and the concepts of leveling and balancing in data flow diagrams. With that, we have come to the end of today's lesson. See you in the next lesson and thank you.